So I first of all thank the organizers for giving me this opportunity to share some of the work we are doing in our group. Fortunate that is coinciding with when Messi is on the ground, but okay, I cannot do anything about it. But okay, I'm going to talk about some phenomenological studies on composite Higgs models that we have carried out in the last few years, and it would have been appropriate to just go to the results, but please bear with me while I share some very basic slides to introduce my results. So as we have now discussed this several times, that the discovery of the Higgs has updated the standard model particle spectrum in a non-trivial sense, because if you assume that the Higgs is an elementary particle, then unlike the chiral fermions and the gauge bosons, it does not have, of course, any symmetry that can insulate it from the UV. This itself is incongruent. And if you further assume that there is a physical high scale that the standard model couples to, this is disastrous and leads to this hierarchy problem. Now, there is, of course, a several multitude of avenues by which this has been addressed over the last several decades. But one very simple possible way out of this pickle is to assume that the Higgs itself is composite. And therefore, in the UV, it basically dissolves into its constituent particle. And you can imagine that in the UV, there are no fundamental scalars at all. So it is just made up of things which can be symmetry protected. So even if you do not care about this argument of composite Higgs as a solution to the hierarchy problem, now that we have the Higgs and we are truly in what we call the Higgs era, I think it's a legitimate question to ask whether this particle that we have found is in point like a fundamental particle, or does it have some non-trivial shape, and which would mean that we can ascribe some kind of a size to it, some kind of a charge radius, if you may. And associated with such a size, of course, would be a scale, which is the compositeness scale of the of this Higgs scalar. And the idea is that below this compositeness scale, the Higgs lives as a composite object of more fundamental particles. Whereas as it crosses this threshold of the compositeness scale, it basically dissolves into more fundamental constituents. And the assumption is that none of these constituents are scalar. And as long as you can generate this compositeness scale naturally, maybe through something like dimensional transmutation, you have a kind of an handle to address the hierarchy problem. Of course, the most natural thing to do would be to assume that all the dimensionful parameters of your theory is connected to this, quote unquote, natural compositeness scale. So you assume the Higgs mass or any other resonances of this underlying strongly interacting theory to be equal to this compositeness scale. And this was, of course, the original proposal of Technicolor models. However, we knew long before the LHC that this wouldn't work out, because from the oblique electroweak observables which were measured at the Z pole at LEP, we already knew that these new resonances would mess up this oblique parameters. And therefore, you need to create kind of a parametric separation between the scale of compositeness and the Higgs mass. Now, one natural way to drive this is to assume that the Higgs is not only composite, but it's also a kind of a pseudo Nambu-Goldstone boson of this strongly interacting theory. And then you have a natural hierarchy between the new resonances, the compositeness scale, and the weak scale. That would survive this electroweak observable test from LEP. So, in some sense, this PNGB Composite Higgs program can be schematically described in this way, that on one end, you have, of course, the standard model with all the elementary particles except the Higgs, and then you invent this strongly interacting sector that is responsible for confining some preons or technifermions into the Higgs. And then the Higgs is actually identified as a Goldstone mode of some global symmetry G breaking to some subgroup H. So you assume the strong sector is responsible for both of these things, breaking the global symmetry and also confining and producing the composite Higgs. Now, of course, even the one way you can give some mass to this Higgs is to invent a kind of a linear mixing between this composite sector and the standard model sector. And this is what is known as partial compositeness. So the idea is that you assume that the strong sector also has some operators which have the same quantum numbers as the resonances of the standard model. In that case, you can write down some linear mixing between these. And since the standard model does not care about any global symmetries of the strong sector, these linear mixings will explicitly break the global symmetry in the strong sector and give a radiative mass to the composite Higgs. So in some sense, the bare essential properties of this strong sector should be that it should produce the Higgs, it should confine some underlying chiral fermions to form the Higgs. But on top of that, it should also be able to have operators which have same quantum numbers, let's say as the colored quarks in the standard model, or maybe even the gluon. So you need, quote unquote, these top partners and these vector partners. In case you are worried as to how this kind of a theory can be driven in the UV, I have just one slide to try to convince you that this is nothing but QCD, which is just again promoted with to another sector. It's a QCD-like theory where you have to just have some fundamental fermions having some confining gauge theory, and that produces a meson, and you basically identify the Higgs as the pion of this new QCD-like theory. Now, again, coming back to the bottom-up approach to this, basically, if you pare it down, the entire picture would look something like this. You, of course, have the weak scale, and sitting around the weak scale is this composite Higgs, which is, of course, made up of some underlying particles. And then in the TeV scale, you have to have all these new resonances which are required for partial compositeness. And then you have the cutoff. Interestingly, these masses of these resonances are linked with the mass of the Higgs, because after all, the mass of the pseudo-Goldstone boson Higgs is generated because of these resonances. Okay, so there's a connection between these two sectors. So if you want to take a pot shot at this picture using the LHC, you have, let's say, 3 prime targets. One is that you can look at the low-lying fruits of these colored resonances, which should show up in this theory around the TeV scale. These are the so-called top partners or the gluon partners, and one can do a direct search for them. The other possibility is that, of course, this Higgs is non-linearly realized because it's a pseudo-Nambu-Goldstone boson. So following the CCWZ construction, it is non-linearly realized, and therefore you would expect, even at the weak scale, that there will be a correlated deviation of the Higgs coupling from the standard model prediction, which would be parameterized by the ratio of the weak scale and the the compositeness scale. However, in my opinion, the best way to look for compositeness of a Higgs is to search for it in the off-shell mode, where you can actually probe the momentum dependence of the Higgs. After all, if the Higgs is composite, then its coupling to other fundamental particles would be momentum dependence, where the scaling is more than the simple logarithmic scaling. And one can probe, if one can probe this aggressive momentum dependence of the couplings, that would be a telltale sign that the Higgs is composite. So this is like doing deep inelastic collision for the Higgs. So I would like to very briefly go through some work that we have done in these 3 directions and very quickly flash some results. So in terms of the searches for strong resonances, this is of course a very large literature on this. The only thing that we try to point out is that if these resonances arise from the strong sector, they would have, because they are members of strong sector, presumably having strong decays within that strong sector, they will have very large widths, and they might start violating the narrow width approximation. And one needs to be careful into taking into account this finite width effect of these broad resonances. So, for example, in this plot, as you can see, this is just some, translation of some collider bounds on the parameter space of some top partner and its decay width to mass ratio. The important thing here is that the solid lines that you can see are the ones where we take the full 1 pi corrected propagators for these top partners, and the dashed lines are the ones which are using the narrow width approximation. And as you can see, when the width to mass ratio is small, these kind of more or less agree. But if you go to crazy high decay widths of the order of 40 or 50% of its mass, you see more than 20-25% deviation in the limits that you would translate using a narrow width approximation, with actually using trying to at least capture the leading effect of the broadness of these resonances. Okay, so we have over a period of time, together with Deeptimoy and Santosh Da and many people, we have worked through many of these, trying to translate them using the full 1 pi propagators. And I don't want to go through each of these slides. The basic takeaway message is just simply this, that at present, the limits on the top partners is, of course, expectedly around 1 to 1.5 TeV, and the limit on the gluon partner is around 2 and 2.5 TeV. But in the what we learned from this exercise is that unless we take the full 1 pi corrected propagator, we make an error of around 20% in translating these limits, and for whatever it is worth. But this, hunting for exotic resonances is probably not the best way to search for composite Higgs, simply because, of course, you have this handle that you can keep pushing this top partner masses upwards, paying in terms of fine tuning. And not only that, there is this classic inverse problem that even if you see these top partners, you never know, what it means, where it came from. It can be from a plethora of models. So the nearly, yeah, well, okay. Okay, with that plot, we went up to 60%. Yeah, no, I agree with you. I agree with you that this is just captures the essence of the broadness, but probably as you keep going upwards, you have to be more correct in including more and more things into it. So that's why maybe, I don't know, somewhere it will start failing again. Okay, so so then moving on to the second very quickly, looking for the correlated deviations in the Higgs coupling that should show up just because the Higgs is non-linearly realized. You can look into the Higgs data. We have now a lot of Higgs data from the run 1 and run 2, and one can check whether you can identify some kind of, because if it is non-linearly realized, you not only expect a deviation of the Higgs coupling, but there's a correlation of how these Higgs would deviate depending on various things like the choice of the coset in the strong sector of which you are assuming the Higgs is a PNGB off, depending on where you embed your fermions. But modulo these things, you would, once you fix these model parameters, you will have a well-defined set of Higgs couplings deviated from the standard model, parameterized by this quantity, which is essentially the square of the ratio of the weak scale and this strong scale. And we did kind of a global fit for the simplest such composite Higgs model, which is known as the minimal composite Higgs model. And the takeaway from this exercise is, again, these Higgs data already pushes these models to about a percentage level fine tuning, which is similar to the status of, let's say, the SUSY models. Okay. And again, just to emphasize that even if we see such a correlated, deviation, maybe in the the updated runs at LHC or maybe at a future Higgs factory, it would still not be a smoking gun signal of compositeness of the Higgs, because all that we can say is that the Higgs has a deviation which is consistent with a non-linearly realized model, and probably nothing beyond this. So finally, let me come to another possibility where you can try to look for the momentum dependence of these Higgs and translate them as a indication for the Higgs compositeness. So if you look at this cartoon, what we have over here is that along y-axis, assume that there is some coupling, and along x-axis, it is, let's say, the center of mass energy. So the standard model coupling, okay, this is in the window of present and future colliders. The standard model couplings would be basically, remaining state. It has very soft logarithmic dependence on the momentum due to RG, but other than that, it would be a, it will scale, in a very, very slowly. Whereas now, if you consider the nonlinear realization, all that it will do is that it will create a shift in these couplings. Each coupling will get shifted, but as long as it is still elementary, it would again, while there will be a shift, it would still scale logarithmically with the scale. So if your Higgs is truly composite and your compositeness scale is in the TeV scale, what you should be able to see is a more aggressive momentum dependence of its coupling, because here the couplings are basically upgraded to be structure functions which have power law dependence on momentum. And if you can see such kind of an scaling of the couplings, that would be in some sense a direct hint of the compositeness of the Higgs boson. So we wanted to do a proof of principle study of whether what can be done in the context of the LHC. So we looked at this HVV coupling. Of course, in the elementary, in the standard model case, it's the coefficient in front of this operator is just a number. And if you think that the Higgs is now a composite object, you have to upgrade this to some kind of a structure function, which, given, energy momentum conservation and in this vertex can depend on two of the momentums in these lines. Okay. Yeah. Yes. No. So just bear with me. I agree with you. So if you put a momentum dependent, first of all, if you put a momentum dependent coupling and derivative coupling, that means it's not the standard model anymore, right? That's already yes. Okay. And so that would already start capturing. So this effective field theory is called the strongly interacting linear Higgs kind of a effective field theory, where you are starting to capture the impact of these momentum dependence in some sense. Yes, but then you have to see how it scales with the off-shellness of the Higgs, and that would be an indication of whether that is included there. So the problem here, of course, is to model how to write down this structure function, because that is non-perturbative physics and it's very difficult to do so. So what we ended up doing is trying to write down what we can using the large N results. So including the 2-point and 3-point functions from the large N, we tried to model the structure functions in this form. Assuming that these coefficients are all, these numerators are all kind of constants. And these masses that show up in this, structure functions, of course, are some parameters of the underlying theory, which is confining the Higgs, but you can, in some sense, identify them with the resonances in this large N dynamics. So these are like, masses or resonances, which are identified with the resonances that build the Higgs up. So using this kind of a very simple-minded parameterization, we tried to look at this channel is associated production of Higgs with a Z, where the Higgs decays to 2 bottom and the Z decays to 2 leptons. And what you see, and we try to look at a bunch of different, observables and check what can be the impact of this kind of a momentum dependent coupling. For a starter, if you just plot the cross section as a function of the center of momentum energy, you see the red line is of course, the standard model prediction, which has to fall off with root of S to preserve unitarity. And what you see over here are these two, this, I don't know, pink and blue lines, which are the kind of variation that you see if you include this kind of a structure functions model with the leading large N results for the structure functions. And this dashed line is the line that you are suggesting, which comes from the strongly interacting linear Higgs, which takes the leading derivative couplings. So this is what you would get from that kind of a scenario. Of course, this is an effective theory. So while the Silch is a very good mimicker of composite Higgs at low energy, it will of course violate unitarity at some scale where the effective field theory fails. A good aspect of using this kind of a structure functions are that they will actually preserve unitarity in the UV. And if you want to concentrate on, let's say, the tails of various distributions, probably this is a more reliable way of modeling them. So using this kind of a framework, we tried to look at a bunch of kinematic distributions, differential distributions of various kinematic parameters, and try to check how it would deviate from the standard model prediction and what are the possibilities to search for them at the high luminosity run of the LHC. So in each of this plot, the red lines or histograms are the standard model prediction, and the pink and the blue is what you get from a composite Higgs-like scenario. And the two lines are assumed. The difference between the two lines is basically we have assumed a broad decay width of these exotic resonances in the propagator. In the structure functions, and in the other case, we have assumed that the decay width is small, around 10% and maybe 40%. So this is why you get these two blue and pink line. So as you can see, for some parameters like the invariant mass of the final state particles or the transverse momentum of the final state leptons, it seems that it's promising and it shows a kind of discrimination. Of course, this is dependent on where your compositeness mass is, what is your compositeness scale, but you can at least hope to see something in this scale. Unfortunately, of course, the present runs for obvious reasons are more focused at the Higgs peak, because that is where you want to look at in this channel. But if this kind of analysis focusing on the tail can be done, we can probably learn a little bit more and constrain the composite, at least if not anything, constrain the compositeness of the Higgs. In this process, yeah, this is the process. Okay. Yes, of course. Well, so if you see here, the way we have modeled this at the level of 3-point functions, we have two resonant masses, and we also assume that they have some kind of a decay width. So we have three independent parameters, the two masses and the decay width, but we have a constraint that this at the low energy should give you the right, the standard model gauge coupling. So essentially it's a two parameter, like two free parameter scenario. Yeah, so I guess this is all that I wanted to say, that that possibly this study for off-shell Higgs is a way forward for these kind of studies. And we are now trying to also look at what happens if the Higgs is in a loop, which has a momentum dependence and has some consequences.
So let us thank the speaker again.